All right, in this video, we move into chapter 4 of your textbook, which deals with some model systems and applying our quantum mechanical ideas to them. Okay, so let's start out by recapping what those ideas are. First of all, we've learned about the Schrodinger equation, right? And we've learned that that's how we get wave functions. A wave function is a solution to the Schrodinger equation, okay? So that's how we generate a wave function for a particular system. We know how to make physical sense, how to interpret wave functions in terms of probabilities, specifically that psi squared tells us the probability density function, right, which tells us where we are more and less likely to find our particle, for example. We know a bit about how to use operators to extract information about measurable quantities, right? If our wave function is an eigenfunction of an operator, then that tells us what is the fixed value of that property. If it's not an eigenfunction, then we can still find the expectation value, which should tell us the average of a large number of measurements of that property, right? Which is still a useful thing. In some cases, those measurements are actually possible, and we can confirm our model by comparing. In other cases, we can use the ideas of the expectation value to generate values for properties we can't actually measure. Things like the position of an electron, for example. We now want to start to use these ideas to describe specific cases, systems, atoms, molecules, what have you, right? In doing this, we very often have to use simplified models. The reason for that is just to keep the mathematics under control and manageable, right? And what we do in this next chapter is we take up a variety of these models. And the first one on that list is the simplest. It's kind of the universal starting point for just about every course that discusses quantum mechanics, and it's something known as the particle in a box model. Okay, our box, at least to begin with, is going to be one-dimensional. So instead of being a box, it's a little bit more like a particle that's free to move on a wire, say, where it just slides back and forth. Right. The little cartoon down there in the bottom of the screen is there's a little blue ball sort of just sitting in the box there, right? As if that's going to represent our particle in the carton. That would be a three-dimensional box, of course, right? The particle it's called the particle in a box because the particle is in the box and it's not allowed out. Okay, how does that actually work? Well, we say the potential energy of the particle, rather, inside the box goes to zero. Okay, so if our particle is an electron, its potential energy is zero as long as it stays inside the confines of the box, between the two limits for my one variable. Okay. The particle can't get out of the box under any circumstances, and that means the sort of fancier way to say that is the potential energy goes to infinity outside the box. And that just means there's an infinitely high wall keeping the particle confined so that it is always between my two boundaries, okay? That's how we put together the particle in a box. We can depict that sort of as an energy diagram where if my vertical axis is potential energy, my horizontal axis down here is just my one dimension, which we've got labeled as x. And we do have the pen. Okay, so if I look down here, this is my x coordinate, right? And my box is defined here so that it goes from x equals 0 to x equals L. That L is not a variable, okay? That L is a parameter, but once we say how big the box is, we've set L, right? L is the length of the box. That's what the L is depicting. This choice of coordinates where 0 is on one of the edges of the box is probably the simplest for working this out, right? Inside the box, my potential energy is 0, so my particle is free to move back and forth anywhere in here, okay? In the walls and outside the walls, so when I get to this green part here on either side, my potential energy goes to infinity, and that just means the particle can't get there, right? Because the particle will not have infinite energy, and so it can never venture over into those regions, okay? This is a little bit similar to how an electron that is attached to an atom is trapped in a fairly small volume of space, right? The atom is little, the electron can't just wander off and be macroscopic distances away, and that confinement, that entrapping of the electron is arguably what causes its energies to become quantized. In this model, the fact that our particle is trapped between these walls will, in fact, introduce quantization to its energies. And so we should get that sort of non-classical result when we actually work through this. The model seems very esoteric and, well, artificial, right? There actually turn out to be some real systems that behave very much in accordance with what this model would predict. One of those is electrons in a pi bonding network in a variety of di molecules, essentially any molecule that has a long chain of conjugated double bonds, right? That's alternating single and double bonds. The ones that are in the diagram there all have rings in them, which does make them a bit two-dimensional. Probably should have drawn one there that just had a long chain of single and double bonds alternating. What happens in those systems is, because you can draw two resonance structures, right? So if you start off with the double bonds here and here and here, and the single bonds in the alternating positions, if you draw a resonance structure, you can flip them so the double bonds go in all the other spots. Right? And because of that, what that does is it means the pi electrons, the ones that are responsible for those double bonds, are actually free to move along the length of that chain. And that's very much like the electrons that are in this particle in a box model. A more modern application, and a real application of this actually, can be found in things related to what are known as quantum dots. Quantum dots are another name for a certain category of nanoparticles. Little bits of matter with dimensions on the order of nanometers, say. The figure there is a collection of solutions of cadmium selenide quantum dots, okay? And those can be grown with their size fairly tightly controlled. The numbers above the vials there represent, actually, I'm pretty sure they're radii of those particles, right? So as those radii go from 2 nanometers up through 4 nanometers, we have the color of those solutions be spanning the visible spectrum, right? It's kind of an unusual property for these small particles, where when you change the size, you change their color. Imagine if you had a block of copper, right, and you got a bigger chunk and it was a different color, or you cut it in half and suddenly it was different colors. That obviously doesn't happen, right? And so this is a peculiar property that occurs only for things in that nanometer size range. These quantum dots actually can be used in things like making televisions. And there are some pretty expensive high-end TVs that rely on quantum dots to be the color generators for the pixels in the image. Samsung in particular is kind of a big proponent of that particular technology choice. So as we start into this problem, a good place to begin is to say, what would happen classically? If we weren't in a quantum universe, what would we expect to happen? So if my box was big and I had just, I don't know, it might represent a ball that was trapped to roll back and forth in a narrow channel, right? So it doesn't actually get to move in the other dimension. It just goes in one variable, one coordinate, okay? And if you did that, and if you had control of the ball, if you could reach in and touch it, you could imagine being able to just stop the ball, and you'd expect it to sit there if there were no forces on it, right? So its energy could go to zero. If you gave it the gentlest of nudges, you could give it some infinitesimally small energy, and from there you could gradually bump it harder and harder, and you could essentially generate any energy you cared to. Right? You would not expect there to be any restrictions on what the energy of that ball rolling back and forth could be. Right? It could go at whatever speed you wanted to have pushed it, and as long as there were no actual friction forces or anything like that, it should stay that way. And that would be the classical picture of what should happen, right? So classically, we don't expect any constraints on the energies associated with the movement of the ball, the particle, right? In our quantum version, we're going to find out that we do get a set of allowed energies, and we're going to have to look at why that, or how that comes about. So how are we going to solve this problem? We start with our potential energy function, which is a little bit of an odd one here, but a simple one. Essentially, we have two regions. One is the part inside the box where the potential energy is zero. The other is the part outside of the box where the potential energy is infinite, right? We use the Schrodinger equation to find the allowed wave functions. And then once we've done that, we'll do that in this video. We'll get as far as having normalized wave functions by the end of this, this piece of video. Then in the next one, we'll take those wave functions and generate the eigenvalues for them to find the energies, right? And then we'll look at what that tells us about the system. So that's our plan of action. So here is my potential energy diagram again. right? Remember that the potential energy goes to infinity for anything that's outside of the box. When that happens, that means the particle is not allowed out there. And that means that in those regions outside the box, starting in the green territory there, I need to have the wave function go to 0, right? My wave function must be equal to 0 out there, because if the wave function is finite, then psi squared is finite, and that would mean there's a finite probability of finding the particle outside of the box. I don't want the particle outside of my box. That's not allowed. And so I need the wave function to be equal to 0 out there. It's gone out of the boundaries of its motion, and that just can't happen, okay? So we only need to think about the part between my limits, right? I've got x equals 0 over here, x equals L over there, and in between there are the only places where the wave function can exist. Remember, there's a rule that says that wave functions have to be continuous. So that means since I need the wave function to be 0 here and here, I also need it to equal 0 when it gets to x equals 0 and x equals L. Okay, I can't have the wave function come in up here and then suddenly skip down to there, right? That's not an allowed behavior. And so I need my wave function to go to 0 at both edges. Right? That's the boundary condition on the problem, and that again is going to be, in some sense, responsible for it becoming quantized. So in between that region, that's where we have to actually find the wave function. This is my Schrodinger equation, okay? What does it say? It says it's only got kinetic energy because the potential energy is 0, right? So that's the kinetic energy operator on the left-hand side acting on the wave function, and it's supposed to give me the energy times the original wave function back again. Turns out we did a version of this when we talked about the so-called free electron problem, right? And we, by assertion, essentially said e to the ikx and e to the minus ikx were both valid solutions to that problem, right? So we could write a general solution as any of a number of linear combinations of those two functions, right? In this version down here, C1 and C2 represent weighting coefficients that dictate how important each one of those pieces is. The ikx and minus ikx exponents, that essentially corresponds to the particle moving in one direction or the other. Right? Those are traveling waves with opposing wave vectors, and so they go in different directions. In order to turn this into something that is recognizably wave-like and useful, what we want to do is we want to get it out of exponential form and into trigonometric form. Okay, to do that, we're going to use Euler's formula, which says that e to the ikx, I can write that as cosine kx plus I sine kx, right? And I can similarly write e to the minus ikx as cosine kx minus I sine kx. Okay, so I'm going to take both of those conversions, those expansions, and I'm going to put them into the wave function. So that's going to give me psi of x is equal to C1, that first weighting coefficient, and C1 is the positive one. I'm going to stop doing that someday, or at least I'm trying. C1 times cosine kx plus IC1 times sine kx. And then I'm going to have plus C2 times cosine kx minus IC2 times sine kx. All right, if I collect up my, my sines and cosines, I can write those and say that I'm going to take the sines first, I think. So I'm going to say I have I times C1 minus C2 sine kx. And then I have plus a piece which is C1 plus C2 cosine kx. And in a way similar to what your textbook does, I'm going to take those coefficients in that one and I'm just going to give them new names. So I'm going to call this C3 sine kx. Plus C4 cosine kx. All right, that's a 4. Doesn't look like it, but it is. So that gives me a wave function down here. Next, I'm going to remember that I need psi to go to 0. Really, I'm drawing a psi, not a t. Psi goes to 0 when x goes to 0. So for that to be true, if I look at this function, that means that I have to get rid of the cosine term, right? Cosine of 0, if x goes to 0, then kx is 0, and cosine of kx then would go to 1, right? So if C4 is anything other than 0, then this function will not go to 0 when x goes to 0, right? So that says that this piece has to vanish. So I'm left with this as what's left of my wave function, right? So my wave function is a sine function, and it's got kx as its argument, all right? Let's pick that up and take it with us over here. So that gives us that we know that psi of x can be written like this, C3 times sine kx, all right? We need also that psi has to go to 0 when x is equal to L, all right? And so because of that, in order for that to happen, and we don't want C3 to be 0 because if C3 is 0, then the wave function is 0 everywhere. And then in fact, I just don't have a particle, right? If the wave function is 0 everywhere, then there's no probability of ever finding the particle, meaning it just doesn't exist. I want a particle in my box. And so in order for this to go to 0 at L, I need the sine function to go to 0. And that means I need KL. I need kx when x is equal to L. So KL has to be equal to n pi, right? Because if kx, or KL in this case, if that's an integer multiple of pi, then I know that sine of KL will go to 0, right? So I can write it this way, where n has to be an integer, right? N is now a whole number. So if I take that, that gives me that k has to be equal to n pi over L, and n has to be a non-zero whole number. So 1, 2, 3, etc. Okay, so that gives me now the beginnings of what my wave function looks like. My wave function now says psi of n, or psi sub n of x, and we'll talk about that n momentarily, is equal to C3 times sine of n pi x over L. Okay, and again, I have the restriction on n from above that says n is a non-zero integer. Okay, so that's my allowed wave functions. Notice that I now have a set of wave functions. They've got this index n in them. That's what we call a quantum number. That is our first encounter with one of those, really. It says that we have this set of possible wave functions, all right? And that any of those should be a valid solution, right? Because they satisfy the boundary conditions. I still have a little bit of work to do to figure out what C3 is there, my normalization constant, to make this a normalized wave function. But that gets me to knowing the form of the wave functions, right? So we've made a lot of progress on that. So these are now my wave functions. My quantum number, again, it just comes from doing the math. We didn't start off, I didn't just say, you know what, I want a quantum number in there because this is quantum mechanics, right? I just said, well, this thing seems like it is a valid wave function for any of those values of n, right? And so I don't just have one single wave function. I have a series of different states, each labeled with its own n value, okay? And that is what it means when we say our problem is quantized. Okay, so suppose we want to go about finding those that normalization constant, right? If I want to do that, what I need to do is I need to make sure that the integral of psi squared across all the possible x values, that has to go to 1, right? That's what it means to normalize my wave function. Right? So here is psi, it's C3 sine the piece we just had, right? I want to find C3 by doing the normalization. My normalization, my limits of my integral here are going to go from 0 to L. That's just because that's the range of values for which the wave function can exist, right? If, in fact, x goes outside of that range, then we know the wave function is 0. Right? So we don't have to integrate out there. I just have dx for my, my volume element because it's a one-dimensional problem, so it's a linear equivalent of volume. That says I'd have C3 squared times that integral of sine squared with the appropriate argument in there to do that. So I'm going to do this by saying, let's just take what the integral piece is, right? If I just take the integral from 0 to L of sine squared n pi x over L dx. If I look at that, I could do a substitution in here. I'd have to do what? U equals n pi x over L and change things to get the limit on things. So let's do that just this once, I suppose. If I say that U is equal to n pi x over L. I won't usually do these because we're not really here to do calculus, right? Du equals n pi, that's a pi. Gosh, that's not a pi, but it wants to be a pi. I swear I just thought I picked, but I obviously did not. Come on, give me the thing, there we go. I would say that I'll get better at this, but the fact is that I probably will not get better at this because I'm afraid I've reached that age. So I have n pi over L dx here. And when I do that, that gives me dx is equal to L du over n pi. The limits of the integral go from, and when I change those, the lower limit stays at 0, the upper limit becomes u equals n pi, and so what I get is the integral of L over n pi from 0 to n pi of sine squared u du. And if we do that, that's 1/2 n pi minus 1/4 sine 2n pi. I'm obviously just copying this off of notes here. Minus 1/2 of 0 plus sine of 0. And all of that gives me L over 2 when I'm done. Okay, so I have the integral piece. This part here is equal to L over 2. What I need is I need C3 squared times that. So I need C3 squared times L over 2 has to be equal to 1, which tells me that C3 squared has to be equal to L over 2. And therefore C3 has to be equal to square root of L over 2. Okay, so that gets me my, my normalization constant for this. If I take that and put it in here in a cleaned up fashion, that says that my normalized wave functions then are psi n of x is the square root of 2 over L times that sine function sine n pi x over L. And again, n is restricted to positive whole number values here. What does this do? It gives us an infinite set of possible states for the trapped particle, meaning it can be in any one of those. There's no limit on how big the n quantum number could get because the walls of my box are infinitely high, so I can keep having additional energy levels up there. But it also means that there are no other solutions than these, right? I can't get a wave function where I put in, say, n equals 1.5 or anything else. So there are some wave functions that are allowed and some that are not. In the next bit of video, what we're going to do is we're going to take that normalized wave function and we're going to work through and find its energy. When we do that, we will prove that there are, just like there are a certain allowed set of wave functions, there's a certain allowed set of energy values. And the particle always has to be in one of those energy levels or another. This is exactly what happens for electrons in atoms, right? Where, again, if we go back to a hydrogen atom idea, your electron, in normal conditions, it sort of should be, or its ground state is with the electron in the 1s orbital. But if I had my atom absorb a photon, it might jump up from the 1s orbital to a 2p orbital or something like that, right? So I could get into some excited state, but I can't get to an energy that doesn't correspond to one of those allowed states. The same is going to be true for my particle in a box model. Thanks.